All right, let's dive into a real classic today, a puzzle you've probably heard of, the Tower of Hanoi.
Oh, yes, a favorite.
We've got a stack of notes here, mainly drawing from Hello Algo
Ah,
to really get into it.
good source for this one.
So our plan is to unpack this puzzle, understand its really elegant solution using divide and conquer,
Mm-hmm.
and figure out why it's just such a fundamental example in computer science. Because it seems simple, right?
The rules are simple, yeah, but the outcome.
Exactly. Simple rules, but surprising complexity, and there's even this cool old legend attached to it.
That's right.
Okay, let's unpack this classic puzzle. First things first, the setup. What are we actually looking at?
Okay, so you've got three pillars. Just imagine three vertical posts. Let's call them A, B, and C.
ABC.
Got it. And on pillar A, you start with a set of disks. Maybe, say, N disks. They're all different sizes.
And they're stacked neatly.
Perfectly. Largest one on the bottom, then the next largest, all the way up to the very smallest disk sitting on top. Like a cone.
Right, okay. So, pillar A has the cone of disks. What's the actual goal here?
The goal is pretty straightforward on the surface.
Right.
Move that entire stack, all N disks, from pillar A over to pillar C.
Just move the whole stack. Sounds easy enough. But there are catches, I assume.
Oh, yes. Three very strict rules you absolutely have to follow, no exceptions.
Okay, lay them on us. What are the rules?
Rule number one, you can only move the topmost disk from any stack.
So no reaching into the middle, just the top one.
Just the top one. Rule two, you can only move one disk at a time.
One at a time. Makes sense.
And rule three, this is the crucial one. A larger disk can never be placed on top of a smaller disk.
Never ever.
Never, ever. On any pillar, the stack must always go from largest at the bottom to smallest at the top. You break that, you've broken the puzzle.
Got it. Top disk only, one at a time, and always smaller on top of larger.
Yeah.
And the notes mention a notation, like FI.
Yeah, that's just a handy way to talk about it. We can say FI represents the problem, or the task, of moving I disks from the source to the destination, according to the rules.
So F5 means moving a stack of 5 disks from A to C.
Exactly, following those three rules.
Okay, where do you even start? That third rule, smaller on top of larger, feels like it locks everything up immediately, especially with the big disks at the bottom.
It does seem that way. That's why starting simple is key. Like the notes suggest, let's look at the absolute base case. What about F1? Just one disk.
Right, okay, one disk on A. What do we do?
Well, think about the rules. Can we move the top disk? Yes, it's the only one.
Correct.
Can we move one disk at a time? Yes. Can we place it on C? Well, C is empty, so putting the disk there doesn't violate the smaller on larger rule.
So you just move it directly, A to C.
Exactly, one move.
Right.
Problem solved for F1. That's our base case. It stops there.
Okay, one disk, one move, easy peasy. But what happens when we add just one more disk? Now we're at F2. 2 disks on A.
Ah, now it gets interesting. You've got the small disk on top of the large disk on A.
And I want to get both to C. But that big one is stuck under the small one.
And you can't move the big one first. Rule one, you have to move the small one.
Right. So where can the small one go? I can't put it on C and then put the big one on top of it later, right? Rule 3.
Precisely. Rule 3 blocks that. So the small disk must go somewhere else temporarily.
The only other place is pillar B, the middle one.
Exactly. Pillar B comes into play. It's the buffer, the temporary holding spot. So step 1 for F2 is move the small disk from A to B.
Okay. Small disk is chilling on B. Big disk is now alone on A.
Now the large disk is on top of pillar A. So step 2, move the large disk from A directly to C.
Nice. Big disk is now at its final destination.
Correct. But we're not done. The small disk is still on B.
Right. Got to get that one over.
Step 3, move the small disk from B to C. Is that allowed?
Well, the large disk is on C, the small disk is smaller. Yes. Rule 3 is fine. Small goes on top of large.
Perfect. And now both disks are on C in the correct order, small on top of large. F2 is solved.
Huh. So that took 3 steps. A to B, A to C, B to C.
3 steps, yes. And notice, we had to use that buffer pillar B.
Yeah, you couldn't do it without it.
And what's really fascinating here, even with just 2 disks, we see the core pattern emerging to move the largest disk in a stack.
You have to get everything smaller out of the way first.
Exactly. Move the smaller stuff, in this case F1, to the buffer. Then move the largest disk. Then
Move the smaller stuff from the buffer onto the target on top of the big one.
you got it, that little dance. Smaller stack off, largest disk across, smaller stack back on. That's the heart of it.
Okay, I think I see that for 2 disks.
Yeah.
But my brain starts to short circuit thinking about F3 or F4 or, FN.
Yeah.
How does this scale? The notes mention thinking of the top N1 disks as sort of a single unit.
That's the leap. That's the recursive insight. It's the divide and conquer strategy applied beautifully here. You don't need to track every single disk individually in your head for, say, F10.
Please tell me I don't.
You don't. You rely on the fact that you already know how to solve the problem for a smaller number of disks, specifically for N1 disks.
So for F3, moving 3 disks from A to C, you're saying we use the solution for F2. How?
Think about that biggest disk again, the third one at the bottom of A, for it to move from A to C.
Everything smaller has to be off A, and C needs to be ready to take it, meaning C must be empty or only have larger disks, which it doesn't yet.
Right. And crucially, those smaller disks, the top 2 in this case, they can't be on A or C when the big one moves. Where must they be?
They have to be stacked correctly on B, the buffer pillar.
Precisely. So the first major step in solving FN from source A to target C is solve the problem of moving the top N1 disks from A to B, using C as the temporary helper pillar.
Wait, so you're doing an FN1 move, but not to the final target C, you're moving them to B.
Exactly. Think of it as task 1. Move the top N1 disks from source A to buffer B, using target C as your temporary workspace.
Yeah.
That's an FN1 subproblem.
Okay, so after that, magically the top 2 disks are now stacked properly on B, and the largest disk is alone on A.
Correct. Now, task 2 is easy. What do you do with the largest disk on A?
Move it to C, its final destination. That's just one move, like an F1 move for the biggest disk.
Perfect. Task 2. Move the nth disk from source A to target C. Now, the biggest disk is home, but
the other N1 disks are still sitting over on B. We need them on top of the big one on C.
which leads to task 3. What do you think that is?
We need to move that stack of N1 disks from B, the buffer, to C, the target, and A is now empty, so we can use A as the temporary pillar for this move.
You've absolutely nailed it. Task 3. Move the N1 disks from buffer B to target C using the original source A as the temporary workspace, and that is another FN1 subproblem.
Wow. Okay, let me recap that. To solve FN, you first solve FN1 to move the top stack to the buffer. Then you move the single biggest disk to the target. Then you solve FN1 again to move the top stack from the buffer to the target.
That's the recursive algorithm. Beautiful, isn't it?
It's incredibly neat. You define the solution for N in terms of the solution for N1. It just unfolds.
It does. And connecting this to the bigger picture, this recursive structure is the key. We solve the problem for N disks by effectively solving it twice for N1 disks, plus that one move in the middle.
That structure, solving it twice for N1, that sounds like it could get computationally expensive pretty quickly.
Ah, yes. That naturally leads us to think about the resources needed. This raises an important question. How many steps does this elegant process actually take? And how much memory, say, on a computer running this recursively?
Let's talk complexity, because solving it twice for N1 sounds exponential.
You're thinking exactly along the right lines. You can picture the process like a tree. A call to solve FN makes 2 separate calls to solve FN1.
Right, like branches.
And each of those FN1 calls makes 2 calls to solve FN2, and so on. It branches out, doubling at each level until you hit the bottom, the F1 base cases.
And the total number of moves is like counting all the operations in that tree.
Essentially, yes. The number of moves is dominated by the number of nodes in this recursive tree. Since it roughly doubles the work for each extra disk, we end up with exponential time complexity.
So formally, what is it?
The exact number of moves turns out to be 2 to the power of n minus 1. So the time complexity is big O of 2 to the n O2n.
O2n. Wow. Okay, so adding just one more disk doesn't just add a few steps.
It basically doubles the entire amount of work you have to do.
Yikes. That explains why it gets hard fast. What about memory? Space complexity. All those recursive calls must take up some space, right?
They do. But think about how the calls happen. When Fn calls Fn1, it pauses and waits. Then Fn1 calls Fn2 and pauses. This creates a chain of waiting calls.
Like stacking plates, the call stack.
Exactly like the call stack. The depth of that stack, how many calls are waiting at the deepest point, determines the space needed. How deep does it go?
Well, it goes from n down to n1, n2, all the way to 1, so n levels deep.
Precisely. The maximum depth of the recursion is n, so the space complexity is determined by that depth. It's linear.
So, ON for space. That's much better than the time.
Much better. It's the time that explodes. The memory needed just grows linearly with the number of disks.
Okay, this exponential time thing makes me think about that legend you mentioned earlier, the one tied to the puzzle.
Ah, yes, the Tower of Brahma legend. It's a great story to illustrate the scale we're talking about.
Tell us about it.
Well, the legend speaks of a temple, sometimes said to be in Benares, India. Inside, there were three large diamond pillars,
Like our A, B, and C?
just like them. And on one pillar, at the beginning of time, God placed 64 golden discs, perfectly stacked at largest to smallest.
64.
Oh,
Okay, so N64.
exactly.
Yeah.
And the monks in the temple were given the task of moving these 64 golden discs from the first pillar to the third pillar, following the exact same rules we've discussed.
Top disc only, one at a time, smaller on larger.
The very same. And the legend adds a rather dramatic prediction
Which was?
that when the monks finally succeeded in moving the 64th disc to the target pillar, the temple would crumble to dust and the world would end.
Whoa. Okay, so based on the O2N complexity, or the 2-in-1 formula, how many moves are we talking about for 64 discs?
We're talking 2 to the power of 64 minus 1 moves.
And the notes give an approximation for that number.
They do. It's roughly 1.84 times 10 to the power of 19.
That's 184 followed by 17 zeros. That's just an absurd number.
It's astronomical. It's hard to even grasp. But let's try. Imagine the monks were incredibly efficient, supernaturally fast even. Let's say they could move one disc every single second.
Okay, 1 move per second, 20 to 47, no breaks.
Even at that impossible speed, how long would it take them to finish?
I have a feeling it's a long time.
The calculation comes out to approximately 585 billion years.
Billion, with a B.
585 billion years.
Okay, so, given the current age of the universe is about, what, 13.8 billion years?
Correct.
We probably don't need to worry about the monks finishing anytime soon then.
Highly unlikely. The world ending, according to that legend, is not an immediate concern.
But wow, what a way to illustrate exponential growth. 64 doesn't sound that much bigger than, say, 10, but the number of steps is just beyond comprehension.
It truly is. It's a stark reminder that algorithms that seem perfectly fine for small inputs can become completely infeasible as the input size grows if they have exponential complexity. That jump from N3 or 4, which you could do by hand, to N64 is just mind-bending.
So let's bring it back. Why is this puzzle, the Tower of Hanoi, featured so prominently? Why is it crucial for anyone learning about algorithms or computer science? You mentioned elegance before.
It really is the perfect storm of simplicity and depth. First, it's perhaps the clearest, most intuitive example of recursion. Defining Fn using Fn1 is recursion in its purest form.
Right, solving a problem by solving smaller versions of the same problem.
Exactly. Second, it beautifully illustrates the divide and conquer strategy. You divide the problem, moving n disks, into smaller subproblems, moving n1 disks, moving 1 disk. Conquer the subproblems recursively, and then combine the results implicitly by the sequence of moves.
And third, as we just saw with the legend, it's a fantastic, concrete way to understand complexity, especially the potentially terrifying nature of exponential O2N time.
It provides that crucial aha moment for so many people. You see this task that seems bewilderingly complex, especially for many disks, and then you see the simple 3-step recursive structure that solves it perfectly.
It makes the impossible feel structured.
Yes. And understanding that structure, that pattern of breaking things down recursively, is a skill that transfers to so many other areas in programming and problem solving. It's not just about this puzzle. It's about learning a way of thinking that you can apply again and again. It's foundational knowledge you'll remember and use.
So we've journeyed from the basic rules through the F1, F2 cases, seen that elegant recursive structure emerge, and then got smacked with the reality of 585 billion years for 64 disks. Quite a trip.
It really highlights a key tension, and this raises an important question. While the Brahma legend is, just a story, the phenomenon it illustrates, exponential growth, is very real. It's a fundamental hurdle in computer science and algorithm design. We often hit walls where a naive approach leads straight to this kind of explosion in computation time.
So as you're listening, think about that. Where else might you see this pattern? Breaking down a big job into smaller, self-similar steps, or encountering situations where adding just a little more input causes the work needed to skyrocket unexpectedly.
And consider that contrast, the sheer elegance and simplicity of the 3-step recursive idea versus the almost unbelievable number of steps it actually generates for a large number of disks. It's a powerful lesson in the beauty, power, and sometimes the practical limits of computation.
Absolutely. Well, thanks for joining us on this deep dive into the Tower of Hanoi. We hope you found that exploration as fascinating as we did.